Okay, moving along with energy, this more deeper look at potential energy and kinetic energy. As a recap, probably encountered these before. Potential energy is stored energy, so things like gravitational energy, chemical, mechanical, nuclear, electrical. Kinetic energy is things like things with motion, so thermal, radiant, sound, etc. So again, key thing we to recognize is that work is just defined as the change in energy. So if I say work done, that could mean that it could be that the kinetic energy changed, the potential energy changed, the chemical energy, just this global thing we look at. To say work is the change in energy. So it's not just equal to force times distance. You have to kind of sometimes relate it to the other equations we know. So for example, we're looking at change in kinetic energy. That's work, but it's also the change in the energy due to motion before. Later on, minus the change in velocity earlier on. So 1/2 mv2 squared minus 1/2 mv1 squared. So we kind of saw this in a previous example last day when there was that excess energy when we were pulling that object, so that changed the speed. So let's look at a few examples. So we have a 145 gram baseball is thrown with a speed of 25 meters per second. So it's starting super easy with this one. So we have kinetic energy is just equal to 1/2 mv squared. So we see that's equal to 1/2. Make sure we have correct units. So we're going to use 0.145 kilograms times the speed of 25 meters per second. So you get an energy of 45 joules. How much work was done to reach the speed starting from rest? Well, it's just the work is equal to the change in energy. So Ke2 minus Ke1. 45 joules is what it currently has. If it was at rest, that means that must have been 0 joules. So 45 joules of energy. And that's our answer. Next question. How much work is required to accelerate a 20 kilogram mass from 40 meters per second to 60 meters per second? Just like what we did. Ke2 minus Ke1. So we're going to have 1/2 mv2 squared minus 1/2 mv1 squared. And what we can see is that if we want, we can simplify this expression. Factor out the half, factor out the m. We get v2 squared minus v1 squared. So that's equal to 1/2 times 20 kilograms. And we have 60 meters per second squared minus 40 meters per second squared. So be careful with this one. It's not 60 minus 40 squared, so it's not 20 squared. It's 60 squared, which is equal to 60 squared, which is 3600, minus 40 squared, which is, so we end up with a value of 2000 times by 20 divided by 2, we get 20,000 joules. So 2.0 times 10 to the 4 joules of energy. That's our answer. Let's do one more. This one, an automobile traveling 60 kilometers per hour can brake to a stop within a distance of 20 meters. The car is going twice as fast, 120 kilometers per hour. What is its stopping distance? And the force is independent from speed. So we're assuming that they were able to apply the same type of force from the brakes for either scenario. So for this one, we have work is equal to force times distance. And that's equal to our change in kinetic energy. Right, so we know that work is force times distance, which is equal to change in kinetic energy. Now we're applying a slowing down force, so like we're going slower, so we're applying some negative work to slow this thing down. So we got negative force times distance. If we're going to reach 0 meters per second, so our final is 0, and our initial is 1/2 mv squared. So what we can see though, when we relate these two together, we get d is equal to mv squared over 2 divided by our force. You can see that what we're trying to relate to is d and v. So what we can see is if v were to double, so d is proportional to v squared. So if v were to double, d has to be 4 times greater. So we need 4 times the stopping distance.